So we're going to review for exam 7, the last chapter exam. And okay. Which will be 2 days from we have a whole week to review for the final. But after you take exam 7, and I've graded it and averaged your scores out and posted them on the Brightspace, you can see whether you have an A or not. It's awful dark. If you have an A, you can skip the final. If you have you don't have an A, let's just put it that way, then you'll take the final, and if the final grade helps your average, I'll keep it, and if it doesn't help your average, I'll throw it out. Okay, so it should lessen the pressure, but I can't justify letting B's, C's, D's, and so forth off, because there's always that chance that you haven't mastered the material yet. But I think most of the people who have A's have big A's, lots of buffer space. So if you've got an A after this next exam, then you can skip the final. As far as labs go, there's Grace. As far as labs go, we won't have a lab, obviously, today. I want to see your notebooks. You don't have to come in to show them to me, but if you don't come in, then you need to scan or photograph every page that has writing on it. Not the whole thing, just the pages that have writing on it. You can, it'd be nice if you can compile them into a PDF, but if you can't, you can submit the individual pages in Brightspace. There's a place in there for you to, in assignments, to submit that work. And then I can give you a final grade on your lab notebook. What I'm looking for in your lab notebook is completeness. Up to this point, I've just been looking at whether you have the sections set up in for each experiment. Now I want to see, do you have everything in there that you've done? And then if you haven't submitted some labs, then get them in as soon as you can. First come, first served. And if you submit something really late, it might not get graded. Let's see, I saw a chat. Hold on a second. Let me check out the chats. Where's the chats? There it is. The answer to your question, Justin, is yes. I know it's splitting hairs, but those are the breaks. Why can't I get rid of that chat? It pops up on the left and then you can't get rid of it. Okay. I think that covers all our class business. So we'll get on to, let's see, did Brittany ever show up? No, okay. All right, so we're gonna, what I've done is, for today's review, I've taken both versions of the some things in two that I felt were important enough that, so I put them together into one document. And the numbering system's the same. So it'll go through. Internet connection is unstable. Oh, that's good news. The numbering systems is the same, and I kept it that way because the worked problems are numbered according to each individual version. It's my habit to run over, so I'm not going to hurry. If you have to go, as usual, go ahead, and I'll just keep going until I finish every problem that I want to. Good, it came back. Especially if it goes to it overlaps into lab. And if you don't have lab, then you may have already made arrangements for that time slot, but I'm going to keep talking and recording. All right. So before I do, yes, question?
Yeah, I'm sorry. This is backtracking, but is the final lab notebook check due today? Or is there like any set time that you want us to turn those in? Did you hear my question, Professor Bly? I cut out whenever I was asking it.
Oh, no, go ahead and try me again.
The final lab notebook check, like where we send the pictures or come in and show it to you, is there a specific date that you want us to do that?
Right, that's not in the syllabus, is it?
No, it's not. I've been looking for it.
Well, I want to give myself enough time to grade, and the grades are due 2 weeks from yesterday, I believe. What would that be? 12th, 13th? Let me see. I do have that. Oh, 19th. Okay, so what if get them to me by Tuesday, the 13th of December.
Okay, thank you.
Okay. This is bugging me. Can I do, it's off screen. All right. So I'm gonna have to let that go. And just walk over to the computer when it's time to page. I don't know why it does that. It could be the program. Okay, there we go. All right. I have something in my hand or I can't talk. So let me scroll down to, I've got them highlighted, the ones I want to check. And let's see, I need to move over there a bit. My goodness, I skipped a lot of it at the beginning. I don't understand why that is. Okay, well, it's like I didn't pick anything from version 1. There we go. So there's not enough of it on the screen. Let's make it a little more. There we go. All right. I think this is in version 2. Version 2, number 1. Which of the following molecules contains a central atom with sp2 hybridization? We're looking for sp2 hybridization. All right, so what you see is in the answers are Lewis dot structures. All right, so that much has been done for you already. You know, if you're going to pick out this hybridization, you got to do the Lewis dots first. And then you look at a central atom. And some of these you've got more than one central atom. You got one here and you got one here. We can even talk about hybridization around here, but we're talking about central atoms. So aluminum or phosphorus, boron, phosphorus again. Chart that I drew for you, how to tell hybridization. The electronic or sometimes they call them effective pairs, will give you sp2 hybridization. So now all you have to do is look at the central atom and discover in the video which of these have 3 groups around it. The first one, both aluminum and phosphorus have 4 groups, so that's out. Right, that's sp3 hybridization. Boron, yep, boron trifluoride has 3 effective groups around the boron, so it's sp2 hybridization. And technically you can stop there. But just so you don't get the central atom that seems strange. Like they would be active. There we go. Everybody's back. I guess we have to get used to it. Our connection is dropping out. Okay. Back to number 3. Consider this molecule in the following hybridization choices. So we have the answers are these different hybridizations: sp, sp2, sp3, dsp3, and d2sp3. What's the hybridization of the carbon atom that's double bonded to oxygen? All right, so we've drawn this one out. 4 carbons. And that one's double bonded to oxygen, and you have, oops. Nope. Carbon, nitrogen. 1, 2, oops. There we go. This one's double bonded to oxygen. This one's chlorine, this one's hydrogen. Okay. So this one is kind of tricky because it doesn't show you any lone pairs. You've got to decide if there are any lone pairs. A trick. Carbon always has 4 bonds or 4 pairs, either bonding or anti-bond or non-bonding. So this one's complete, and you can count for octets too. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, oops. Sorry. There we go. 2, 4, 6, 8, 2, 4, 6, 8. Okay. But nitrogen only has 6. So it's got to have a lone pair here. Because we know nitrogen doesn't exceed or doesn't fall short of an octet. Now that's if I get tricky and I change the parameters of a question like this and say, instead of focusing on that one, what about that? Right? That's why I'm going to all this detail, because I could be devious, change the question around. But for this one, the carbon that's hybridized with this carbon, that carbon, and that oxygen has 3 groups, which means sp2. So sp2 hybridized. While we're at it, that one's 4, that one's 4, so this one's sp3, this one's sp3. This one is sp, 1, 2 groups. And this one is sp, 1 on this side, 1 on that side. Okay. All right. So the answer to this one's B. I wonder what 4 is. Looks like it's using the same molecule. Oh, yeah. What's the hybridization of nitrogen? And I showed you that one. That's sp. So you got 2 for the price of 1. And 5. Consider this molecule. Specify the hybridization of each carbon atom in the following order. All right, from left to right, 1, 2, 3, 4, 5, and they're numbered. So I'm going to save time and not draw it up on the board. Notice that how many groups around each one, right? And remember when you write this, I forget the proper term for it. You write organic molecules like this. When you have a hydrogens attached to a carbon, if they're between the carbon and another carbon, that means this hydrogen is attached to that carbon, not to the neighbor carbon. Right? So when we write them like that, we have 1, 2, 3 on that carbon, which is sp2. So all of these are sp2, so you got to consider all of them. This one has 2 groups, no 3, 1, 2, 3. It's also sp2. All right. So we can consider A, B, C, D. And this one is sp2 also. So you got 3 sp2s, right? So we're stuck on A or B. This one is 2 hydrogens and 2 bonds on either side is sp3. Right? So both of these are sp3. So we got to go to the last one. That's the tiebreaker. So this carbon has 1 on this side, 1 on that side. That's sp. So it has to be A. Okay. Feels like we're beating a dead horse, but the more problems you work, the better, the more comfortable you'll be with this stuff. So we'll just keep doing a few of them. How about this one? The hybridization of selenium in selenium hexafluoride. So for this one, we did not give you the Lewis dot structure. You have to do it yourself. So selenium is in chalcogens. It's oxygen's group. It has 6 electrons. Fluorine is a halogen. It has 7 each times 6. So that's 42 plus 6 is 48. 48 electrons. Got selenium in the center, and we have 6 fluorines. Okay. So 2, 4, 6, 8, 10, 12 we've used up. Right. So we have room for 6 more around each of the fluorines. Use them all up. I'm not going to put all the dots around here. Each fluorine has 6 non-bonding electrons. That means that we don't have any electrons that we had to add to selenium. So this is everything that's around the selenium. 1, 2, 3, 4, 5, 6. 6 groups means octahedral, which also means you need 6 hybrid orbitals, right? If we do sp3, that's only 4, right? So we need, excuse me, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay. Any kind of bond at all, it's got to have 1 sigma. Why this thing won't stay pinned to me? Okay. And whether it's the valence bond theory or it's hybridization, you can't have any more than 1 sigma. So how do pi bonds form? Well, they can't form on axis, right? So they have to form from orbitals that are off axis. And for our purposes, we're talking about primarily p orbitals. You can do it with other orbitals, but that's advanced. So if we overlap off-axis p orbitals, we can get a pi bond. All right, so let's see which ones of these fit. Overlap of 2 s orbitals. No, s orbitals have to be on axis because they're spherical. Overlap of an s orbital and a p orbital. The only way you can get that is a sigma bond, because you're going to have that one here and maybe this one here, like that. You get overlap on axis. You can't do off axis with s orbitals. Overlap of 2 p orbitals along their axis. Now that's a sigma bond too. If it's on axis, let's get kind of messy, but on axis means sigma. Sideways overlap of 2 parallel p orbitals. Yep. Overlap that one, and that's part of the same system. So that's how you get a pi bond. We're not going to mess with E because It's just a filler. All right, number 9. Let's see, can I get both of them? No, I can't. Number 10. I'm gonna need a fresh marker, it looks like. Please here from whoever else shows up. Here we go. Use the molecules below to answer the next 3 questions. All right, these molecules are written in organic shorthand. That's a ring structure. And wherever 2 lines meet is a carbon. So we don't write the carbons. It's understood there's a carbon right there. Then we write single or double bonds between the carbons. And we also don't write the hydrogens. That's why I think we put the formulas in there. C6H6, C6H8, and C6H10. So what we've got here is double, double, double. And then each one of these carbons has a hydrogen on it. That's where you get the 6 hydrogens. Right? So 1, 2, 3, 4, or an octet for each carbon. Doing it that way. If we do it this way, then we've got a double here and a double here, and 2 singles there. So that means we have a hydrogen there, hydrogen there, hydrogen there, hydrogen there, and we have 2 here and 2 hydrogens there. Okay, that gives you 2, 4, 6, 8, octet. And then for this one, we only have 1 double bond. So we have a hydrogen here, and then 2 for each of the others. That accounts for all the hydrogens. Now the question is, which molecules have p orbitals that share an electron pair to create pi bonding? Whenever you see a double or a triple bond, you have pi bonding in that between the atoms. You've got a sigma. Here's just a sigma, nothing else. Here's a sigma and 1 pi. Right, so each one of these has a sigma, 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 and then a pi here, a pi here, and a pi here. So each time you have a double bond in this system, you've got 1 pi. So the one on the far right has 1 pi bond. This one has 2 pi bonds, and this one has 3 pi bonds. So which molecules have p orbitals that share an electron pair to create pi bonding? Well, all of them do, right? This one has more than those, but they all have pi bonds. Now, with those same structures, I think 11 asks a different question. And I'll do it like that. 11 asks, which molecule that over that ring structure, that makes every bond equal in length and strength. But here, we can't do that because we've only got a one double bond here with single overlapping p orbitals. Right? We can't do that over here because those orbitals are used up. So these bonds are different. This bond is shorter than that one. And it's the same as this one and that one. And there may be some delocalization here. Right? But the question is, have equivalent carbon-carbon bonds throughout the molecule. Right? Because they can delocalize. These are not. And this one only has one double bond. Okay, what does that do for the stability of the molecule? The more you can delocalize electrons, the more stable the molecule, and the stronger the bonds overall. So that means this one would be have bonds with the strongest bonds in them. These would have different length bonds here and here. These would be shorter bonds. These would be longer bonds, which puts a stress on that ring structure. Right? It tries to move out here and contract here. It moves out here and contracts right there. So this is the most stable one because of that reason. E. Wait. Which molecules have equivalent carbon-carbon bonds throughout? That's the wrong answer. That's not right. That answer should be A. They have equivalent. All right. If you didn't know about delocalizing electrons in the bonding system, then you would have a tendency to say none of the above have equivalent carbon-carbon bonds. But since we do know about delocalizing electrons, these bonds are all equivalent. That answer should be A. I don't know if I can change it here. Yeah. There we go. Whether it'll let me save it. No, it won't let me save it. That's all right. I better make a note of it though. Let's see. 11. Here we go. 11. It should be A. All right. Uh, 12. And 13. Got them both up there. Well, all right. The electron configuration of a particular diatomic species is this shorthand. Right now we're into molecular orbitals. What is the bond order for this species? When you write out this shorthand, it tells you which ones are bonding, which ones are anti-bonding by the asterisk. So you add 2, 4, 8 bonding and 2, 4 anti-bonding divided by 2. It's bond order of 2. All right. So there's no direct correlation between them, but a bond order of 2 generally means it's a double bond in that system. Let's see, where am I? Here we go. All right, that was 12. How about 13? As the bond order of a bond increases, okay, so if the bond order is increasing, what else is going on? What happens to the bond energy? And the bond length. Right? As the bond order increases, the energy increases. And that draws the atoms closer together. So the bond length decreases. So increase, decrease should be the answer, which is C. right? And if it goes the other direction, right, you just flip these around. Bond order decreases, then the bond energy decreases, and the bond length increases. It's just that simple. All right. Let's see, 15. How many unpaired electrons in the difluorine 2+ ion are based on molecular orbital theory? How many unpaired electrons are there in this molecule? Okay, and we've also, in this case, given you the order of the orbitals, so you don't have to look them up. You could look them up. All right, they'll be in useful information, right? In fact, it's on the back page here, right? You'll have these difluorine here. And incidentally, difluorine has no sp mixing. So if we write out as given, say 2s, and then sigma star 2s, and then sigma 2p and pi 2p, and then pi star 2p, and then sigma star. That's the way you write no mixing. If there were mixing, then these two derived from p orbitals would flip. Okay, so how many electrons do we have to put into this system? We may not need all of those orbitals. Right? Remember, this one's got 1, 1, 1, 2, 2, 1. I think that's right. Yeah. Okay. So 2 fluorines would be 2 times 7 is 14. But that's neutral. We lost 2 electrons. So there are only 12 electrons that have to go into the system. And if we use Hund's rule and the Aufbau principle, lowest energy to highest energy and unpaired in degenerate orbitals before you can pair them up. Okay. So this one is by itself, by itself, by itself. And then this one, 2, 4, 6, 8, 9, 10, 11, 12. So we didn't even need this one. So we have 2 unpaired electrons. Okay. So what does that mean for its behavior in a magnetic field? Is it paramagnetic or diamagnetic? Well, paramagnetic has unpaired electrons, at least one. Diamagnetic has all paired electrons, which means the unpairing of electrons causes that species to be drawn into a magnetic field. Whereas paired electrons, all paired, means it's repelled by that. I think I read something not too long ago about if you, all the water molecules in your body are diamagnetic, all paired electrons. So that means they repel a magnetic field. If you put a frog into a very strong magnetic field, he'll levitate because he's repelling the magnetic field. Whereas our bodies are what, 78 or 9%, something like that. Internet. I'm gonna have a talk with the folks down the hall. It won't do us much good. this semester. But if I can get one or more of these ports active, then we can go hardwire from now on. Well, it might help if y'all come back next semester. Yeah. We won't have to deal with this squirrely internet. Okay. 19. All right, hybridization of the central atom of ClF2 plus. ClF2. 1 plus? Yep. Okay, so we have to draw the molecule. Right? We've got 7 electrons here, 7 times 2 there, because they're both halogens. But we're missing 1, -1. So that's 21 minus 1 equals 20. 20 electrons. Chlorine's in the middle. Fluorine, fluorine. 2, 4, 16. 2, 4, 6, 8, 10, 12. We got rid of 12 already. That leaves 4. So where do we put the 4? We already got an octet here, or we got 1 here, 2 there, 2 there. Okay, so that 14, 16, 18, 20. And remember, if you don't put that bracket with the charge on it, then you cannot accurately count up the electrons and know that they're balanced. Right? Now, right? So that's only 6 around each carbon. By drawing the Lewis dot structure. You don't know that carbon always has 4 electron pairs around it. And this one does have a pi bond. Right, it's got a double bond right there. When a pi bond. This one does not. Formaldehyde, I think this is what this is. Carbon in the middle, oxygen, 2 hydrogens. Yeah, that's formaldehyde. There we go. So 1, 2, 3, 4, 1, 2, 3, 4. We're good. And that one's got a pi bond in it. So the only one that doesn't have a pi bond is this one. D. All right. Scroll time. So let's stick it there. 24. Complete the Lewis structure for the following molecule. This molecule has so many sigma bonds, so many pi bonds. So if we draw it out like this, and notice all of these, well, the hydrogens are from the period 1, but the rest of them are from period 2. And from the far right, from carbon over, which looks like it covers everybody in that group except hydrogen, they're very well behaved with the octets. That's good to know. And this one's got a methyl group up here, and a carbon, and a carbon, and a nitrogen. And this one has an oxygen. It's not complete yet. So let's take this one and expand it. Hydrogen, hydrogen, hydrogen. That's what that means right there. This one is down here like this. Okay. All right. So let's go ahead and do the Lewis game ourselves. 1, 2, 3, 4, 5 carbons means 20. 5 times 4 is 20. Yes. Oxygen is 6. And nitrogen is 5. Yeah. And then hydrogens. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Plus 7. Okay, so how many electrons do we have? 31, 38. 38 electrons. Okay, that's already got an octet. That's an octet. That's an octet. This one's not an octet. But we have to start from the outside and move in. Wait, we've got to count the bonds. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All right. Now we know how many is left over. 12 electrons left over. 2, 4, 6. Right, 6 electrons. 2, 4. And that's 2. So we'll put 2 here. Yeah, I don't think we have enough electrons up there. 2, 4, 6, 8, 10, 12, 14, 16, 18. 20, 22, 24, 26. That's right. And the bonds. Total 38. Okay, 1, 2, 3, 4, 5, 20. And then oxygen is 6. And nitrogen is 5. That's right. And then 1, 2, 3, 4, 5, 6, 7 hydrogens. That's right. And 12, 18, 38. Okay. 12. All right. So we just put 6 here. That left 6. 2, 4. Oh, okay. Here's what I did wrong. I put that lone pair there, and it should go here. Actually, it needs to be there. Oh, here's another mistake I made. Work from the outside in. I started putting electrons on these. These are inner electrons. This is an outer, right? This is outer. So let's do that again. Let me do it right this time. All right, so we got 12 electrons to place. Right. 2, 4, 6. 2, 4, 6, 8, 10. Then we can move in and put, I don't know, what. There we go. Now we've got all our electrons on there. Okay. This one doesn't have an octet. That one doesn't have an octet. This one has an octet. But we're going to use a lone pair Actually, this one needs to be over here. Because we're going to use these to go here, here. Okay, that still gives you an octet there. This one has an octet already, so it doesn't have to go that direction. But we're going to use this one to go here. All right, so if I do that and remove those, okay. There we go. So now that we have those 12 electrons still. 2, 4, 6, 8, 10, 12. Yes. All right. That's not the easiest Lewis dot structure to draw. I'll grant you that. But to answer your questions, how many sigma bonds do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. 13 sigmas. How many pi's? There's a pi, and there are 2 pi's. 3 pi's. So it's 13 to 3. I mentioned earlier that carbon generally forms 4 bonds when it can. Carbon usually, oxygen usually forms 2 bonds with 2 lone pairs. Nitrogen same atom, or it can form 3 like that for ammonia. And oxygen, good example of oxygen is water, 2 bonds there. But it'll also form 2 bonds with other atoms as a double bond. These are just trends that you pick up. And they can save you time when you're solving problems using those atoms. Okay, 4. Okay, 26. Consider the skeletal structure below. Draw the Lewis structure and answer the following question. How many pi bonds does the molecule contain? All right. It doesn't say are there any other atoms connected with it? And we have to assume that there are no others. This is it. All right, so we have 2 times 4 is 8, and 2 times 5 is 10. So we have 18 electrons. All right, 2, 4, 6. That's 12 electrons left over. 2, 4, 6, 8, 10, 12. All used up. Okay, now we have to make an octet. So if we these carbons need 2 more, right? So if we do this and this on both sides, we get like that. Okay. So that means we have how many pi bonds? Okay, 1, 2, 3, 4. 4 pi's. How many sigma bonds? 1, 2, 3, just like we started with. 3 sigmas. Okay. I'm trying to think what that molecule is called. It escapes me at the moment. Which of the following molecules contains the shortest carbon-carbon bond? All right. All of these molecules, well, we're going to have to write them out. C2H2, C2H4, C2H6, and C2Cl4. All right. This is 2 carbons together with 2 hydrogens. Right? So in order to make the octet here, we need a triple bond. Right? And you can draw the Lewis dot structure and prove it to yourself. This one we did before. That's a double bond here with 4 hydrogens. Okay, and this one we did before also, and it's got 6 hydrogens. Okay, this one, let's go ahead and do the Lewis thing for this one. 2 times 4 is 8, and 4 times 7 is 28, which means 36 electrons. So we've got carbon to a carbon, and then we have a chlorine and a chlorine. So 2, 4, 6 is 30. That's 12, and which is 18. Okay. C2, Cl, oh, Cl4, excuse me. That's another 12. 6 electrons. Now we can put the other 6 in here. I think. If I counted right. No, I didn't count right. 2, 4, 6, 8, 10. 26. There we go. So we have 2 electrons left over. These all have their octets. This one, we need to make an octet for this one and that one. So we're going to take that one and make a double bond out of it. Okay. So now everybody's got an octet. Now, what's the question? Which ones have the shortest bonds? Well, the shortest bond is going to be the one that's the strongest. That means the one that's got sigmas and pi's. And the most pi's are this one. 2 pi's and 1 sigma. This only has a sigma and a pi. This one only has a sigma. This one has a sigma and a pi. It's like this one. Not exactly like, but close. So this one would have the shortest bond. Be the strongest bond. That's acetylene, by the way. All right. Okay, we did those, both of those. Let's see, I can get those 2, 28. Yeah, I told you I was going to run out of time. When comparing Be2 and H2. All right, if we look at the choices here, Roman numeral 1 through 4, we're talking about molecular orbitals. Okay, so what's the structure for H2 is the easiest one. It just has a sigma 1s and a sigma star. Yes. Right, so we got 2 there and actually none here. Beryllium has actually sigma 1s, sigma star 1s, and then it has a sigma 2s and a sigma star 2s. And beryllium has, let's see, total electrons it has 8. So if we put 2 here and 2 here, that's 4. So we have 4 more. We can have 2 here and 2 here. Well, that means that's no such thing. Did I do that one right? I better look it up. Yeah. So beryllium has 2s, sigma star, and sigma star. Okay. And it has or 8 electrons. All right, so what's the question? Beryllium-2 is more stable because it contains both bonding and anti-bonding. Well, no, that if it has anti-bonding, it destabilizes it. Hydrogen has no anti-bonding electrons, so it is more stable. H2 has a higher bond order than Be2. Yeah, it does. In fact, if we calculate the bond order here, it's 0, and here is 1. H2, in fact, we predict this one doesn't even form. I don't even know why it's on here.
What is it?
Yeah,
exactly. How you doing?
3. Roman numeral 3. H2 is more stable because it only contains no. Stability has to do with the bond order when you're talking about molecular orbitals. H2 is more stable because it is diamagnetic, whereas Be2 is paramagnetic. No. Now, why does the answer say Roman numeral 3? H2 is more stable because it only contains. Well, okay, I see what they're doing. It only contains bonding electrons, whereas beryllium contains bonding and anti-bonding electrons. Okay, so I see where Roman numeral 2 and 3 could be considered correct answers. How about the last one? Is that true? H2 is more stable because it's diamagnetic? Yeah, it's diamagnetic. Those are paired. But Be2 is not paramagnetic. It's also diamagnetic. Qualifies 4 and 1. I hope that made sense. 29. Which of the following species is paramagnetic? All right. So C2, O2, F2, and Li2. All right, so I'm going to get some help here. Let's see, carbon is going to be sp mixing. Yeah. Lithium is sp mixing. Fluorine is no. And oxygen is no sp mixing. Okay, so we're going to have carbon is, and I'm going to 2s sigma 2s star. We're gonna leave out the non-valence electrons, and then pi 2p. There. So carbon has 4 valence each, which means 8. 1, 2, 3, 4, 5, 6, 7, 8. It's all paired. Oxygen. Oxygen is, let me see, the question was, which following species are paramagnetic? So this is diamagnetic. Oxygen. You know what? When you're taking a test, you don't have to draw these things out. Look at this chart, right? Dioxygen. Dioxygen, going down here, you have a pi 2p star with 1 electron each. That's paramagnetic. Fluorine has the same thing here. The same orbital is its terminal, but it's got filled paired electrons, diamagnetic. In lithium, we look back at lithium. Right, so I have to draw lithium because it's not here. Well, it does give the order. Sigma 2s, sigma star 2s, and pi 2p. star 2p. That's probably all we're gonna need. Like, well, lithium it only has two valence electrons. Right there. So we didn't need all those. This is a diamagnetic. All right, they're paired. All these other orbitals is because if you start adding electrons, like making ions, then they got to go somewhere, and they're going to go in that order. All right. I'll have to scroll down to get 30. See if I can get 32. Yeah. Okay, 30. For how many of the following does the bond order decrease if you add one electron to the neutral molecule? So we're looking for a bond order decrease. A bond order decrease if one electron added to the neutral. And so we got diboron, dicarbon, diphosphorus, and difluorine. Okay, so here's a case where you can use the chart and look at each one. The diboron has its highest orbital has pi 2p, and it's got one each. Okay, here's the trick. If you add electrons to a bonding orbital, you strengthen the bond. You increase the bond order. So we're looking for a decrease. If we add an electron here, then that increases the bond order. Because of the formula, you're adding more bond. The carbon, its maximum is actually full, 2p. So the next one up is a bonding orbital, right? You add an electron there, you increase the bond order. Phosphorus. Phosphorus is going to be like nitrogen. So nitrogen has a sigma, and then in phosphorus case, it'll be a 3p, not a 2p. 3p with 2 electrons in it. And then the next possible one is pi star 2p. So if you add an electron, you're adding it in here to an anti-bonding, that decreases your bonding order. We didn't have any wonky ones, did we? Oh, it said, how many of the following does the bond order decrease? Okay, so we got one so far. How about fluorine? All right, fluorine's top one is a 2p star. Right, and it's full for the neutral. The next one above that is a sigma 2p star. Right. If we add one in there, we've added to an anti-bonding, it decreases the bond order. So these two, we decrease the bond order by adding an electron, which makes the answer C. Okay, that's how you do it quick, rather than have to draw it all out. You get the same information as long as you have this chart, or you have a good memory. Better than mine, but that was 30. Still recording? Yes. Okay. 32. Order the following from shortest to longest bond. Don't forget the effect of atomic radius and orbital size. All right, so we got 2 carbons, diboron, dihydrogen, and dinitrogen. So we're looking for the from shortest to longest. So we want to go short to long, which means strongest to weakest. As far as bond strength goes. But we may also have to consider which orbitals they're coming from. Right, so let's look at carbon. We might have to draw these out. All right, so I'm just going to do that. Right, these are the valence. Carbon, here we go, carbon. Sigma star 2s and pi 2p. All right, so this one has that's 4. Okay, boron. Boron is same order. Only boron has that one, that one, that one, that, like that. Okay. Hydrogen. Well, hydrogen's going to have just the sigma 1s. That's it. And nitrogen. Nitrogen has this one, this one. Maybe I better draw it out since I stuck that one in the middle. And pi. Yeah. Nitrogen has, oh, it also has sigma 2p. All right. So there's 1, 1, 2 here, and 1 there. And they're all full. Okay. So let's calculate bond order first. Bond order here. We have 2, 4, 6 minus 2 divided by 2 equals, excuse me, is that right? 2, 4, 6 minus 2. Yes, is 3 divided, it's 1.5. Bond order. Okay, bond order here. 2, 3, 4 minus 2 divided by 2 equals 1. And this one is bond order. Bond order equals 1. And this one is 2, 4, 6, 8. 8 minus 2 divided by 2 equals 3. Bond order 3. Okay. Shortest to longest bond. Well, we know that the shortest bond is going to be, well, notice also that these are formed from the second period or the second principal quantum number orbitals. So they're going to be farther out from each molecule. Now, when we're comparing second level, second level, second level, we can put these in order, right? This one's going to be the shortest of those, right? And then this one's going to be the next one. So shortest to longest, right? Shortest, and then carbon, and then boron. But where does that leave hydrogen? Well, hydrogen is formed from 1s, right? Those nuclei can get really close together before the 1s, the sigma 1s's overlap. Well, I shouldn't say that because that assumes that they're atomic orbitals, and they're not. They're since they're formed from this level, n equals 1, then those hydrogen nuclei can get really close. So hydrogen is going to be the shortest one. Then nitrogen, then carbon, then boron. Okay, see my reasoning? We can compare these based on bond order. And the higher the bond order, the shorter the bond, as long as they're working from the same level of molecular orbitals, second level. But when you get to orbitals that are formed from atomic orbitals that are even closer and closer together, lower energy. And it goes. I don't know if it lost that last one, but I've erased it. I don't have time to go back. Which of the following has a bond order of 1.5? We're looking for bond order 1.5. So our choices O2 plus, N2, O2 minus, and C2. Okay, so let's do the neutrals first. I mean, let's just write them as if they were neutral, and then we'll do the ions. O2. O2 has sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p. Okay. This one has that. This one has full. This one has full, full, and full. Okay. We haven't made the ions yet. N2. N2 is sigma 2s, sigma star 2s. Then we go to pi 2p. Then we go to sigma 2p. Actually, we don't have to do this. We know the bond order of dinitrogen. It's 3. We know the bond order of oxygen too, which is, this one is 2. Well, neutral is 2, right? So we better do that, right? So oxygen is going to be this one here, 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 here. And that's that, 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 that. And this one has lost an electron, so we take one away from here. All right, and the last one, carbon. Carbon is going to use this scenario. All right, it has nothing out here. We don't need that. And these are all full. All right. So the bond order of carbon, since it's neutral, we'll go ahead and do that one. Right? 2, 4, 6, minus 2 is 4, divided by 2 is 4. Oh, excuse me. Divided by is 2. All right. All right. So we don't have to mess with those. These, the bond order here for oxygen starts out at 2. Starts out at 2. But notice with this one, we have subtracted one of the anti-bonding, which bumps it up by 1/2, right? Because we lost 1 electron divided by 2, which is 1/2. This one, we're going to add an electron. So where are we adding the electron? Oxygen, here, here, here. All right. Not to get that confused with this one. This one is based upon that order. Right? So now if we're going to add an electron, it has to go into an anti-bonding order, which decreases this one by a half. There's your answer. O2 minus is bond order 1.5. That's C. This is one of those things, these types of problems where you need to work a lot of to get comfortable with it. Some things you can pick up just like that. But this stuff, I don't know about you, but for me, constant repetition is the only way to get comfortable with it. Okay, so which statements below are false for that diatomic molecule? And we assume sp mixing, right? Which makes sense. Both boron and nitrogen are left of that dividing line. Right? So both of them experience sp mixing. As dinitrogen or diboron, they would be sp mixing. So when we put these two together, there's going to be sp mixing. All right, so what we would do is we would say boron has 1, 2, 3, nitrogen has 5, so we have 8 valence electrons, which means we're not going to use the 1s derived molecular orbitals. We're going to start with the 2s's. Right. So we have 2s, star 2s. Mixing gives us pi first. Yeah, pi 2p. And sigma 2p. And then pi star 2p and sigma star. Okay, so there's 1, 1, 2, 1, 2, 1. All right, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. All right, that's it. Okay, so what can we say? We don't need these. Well, let's calculate the bond order. 2, 4, 6 minus 2. 6 minus 2 divided by 2 equals 1.5. All right. Is this paramagnetic or diamagnetic? This is diamagnetic. All paired electrons. A is false, right? A is false. Well, we found our answer, right? Because the E says all of these are true. We found the false one, right? Which of the following statements about the molecule being is false? Well, wait a minute. Its bond order is 2, 2, 4, 6. Oh, excuse me. No, that's right. No, that's right. That's right. 6. 2, 4, 6 minus 2 divided by 2 is 1.5. So B is false also. A and B are both false. Right? Two, 4, 6, 3 plus 5 is 8. That's right. Yeah, that's right. 2, 4, 6, 8. So it's diamagnetic, not paramagnetic. Its bond order is 2. No, its bond order is 1.5. No, it didn't. Oh, where's my brain? 6 minus 2 is 4. All right, so that one's true. C is probably true also. Total number of electrons is 12. 2, 4, 6, 8. The total number of electrons, right? It didn't say valence electrons, it says total number of electrons, which means 8, and there are 4 electrons we didn't need to put in there. Right, the 1s shell has 2 electrons each, which is 4. 4 plus 8 is 12. So this one's true. And then D, it has 2 pi bonds. Well, here's 1 pi, here's the other pi. It's better to do it this way. All right. So we found the right answer is A. (37) and 38. Which of the nitrogen containing molecules below is paramagnetic in its lowest energy state? Paramagnetic. All right. O, H3, N2, H4. You know what? We only spent time on homonuclear diatomics and a couple of heteronuclear diatomics. These are polyatomics. And actually, that's not even right. Because this one is paramagnetic. No, this one's diamagnetic, excuse me. All paired. NO. This one's also diamagnetic. No. We got 5 and 6 is 11. 11 electrons. So 2, 4. Nitrogen and oxygen. It doesn't even say if we use mixing or not. And in this case, mixing would be significant. All right, I'm going to throw this one out. That's beyond this. So you won't see one like that on the exam with polyatomic molecular orbitals because we didn't spend any time on them. Let's move on. Which of the following molecules or ions is not paramagnetic in its ground state? In its ground state. Well, lowest energy state. That's what that means. Ground state means even if it's an ion, all the electrons have to be packed in, right, at lowest possible energy. So O2. Okay. If we look at O2 here, we find that it has 2 unpaired electrons. It's diamagnetic. If we have O2 plus, this is O2. O2 plus, we take away an electron, but it's got 2 unpaired electrons. So we take away one of them, it's still got an unpaired electron. That one is still diamagnetic. And I'm just looking at this right here, showing me the structure. molecular orbital structure. B2 has 2 unpaired electrons. It's diamagnetic. No, it's paramagnetic. Not paramagnetic. This is paramagnetic, unpaired electrons, unpaired electrons, unpaired electrons. How about D? NO. It says assume no mixing. Right. So on that previous one, we could have used no mixing, profiling that NO. So on this one, we've got 2, 4, 6, 8, 10. Excuse me, 5. 5 and 6. And we've got sigma 2s, sigma star 2s, sigma 2p, pi 2p, and pi star 2p if we need it. Okay. So this can have 2 paired. This one can have 2 paired. We've got 11. This one can have 2, so that's 6. We've got 5 more. This one can have 4, and they're all paired. And then we've got 1 left over. So this one is paramagnetic. And then F2, how about F2? Well, if we look at F2 on our chart, they're all paired, right? This is diamagnetic. That's why E is the answer. Okay, I hope I didn't confuse anybody. I almost confused myself. CO, that's 4 here, 6 here, that's 10 electrons. And assume mixing. So we're going to have, I want to write shorthand version. Sigma, sigma star. And then pi star 2p and sigma star 2p if we need it. And so we got 1, 2 there, 1 there, 2 there, and 1 there. 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Electrons occupy anti-bonding orbitals. No. A is false. The highest ones occupy bonding orbitals. 6 molecular orbitals contain electrons. 1, 2, 3, 4, 5. Right, so B is false. C, there are 2 unpaired electrons. Nope, there are no unpaired electrons. They're all paired. D, bond order. We didn't calculate that yet. So there's 2, 4, 6, 8 minus 2 divided by 2. See if I can do this now. 8 minus 2 is 6 divided by 2 is 3. That one is true. Okay. So D is the answer for this one. (41) Which of the following statements about CO3 2 minus is false? CO3 2 minus. What is that? That's the carbonate ion. All right. Let's see. What are we going to have to do with it? All right, it's got a mix of valence bond theory and molecular orbital theory. The first one is valence bond. Orbitals on the carbon atom are sp2 hybridized. All right, so we're going to have to draw, let's see, 4 electrons here. 3 times 6 is 18, plus 2 more. So that's 24 electrons. And carbon, oxygen, 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 2, 4, 6, 18. 2, 6, 2, 4, 6, that's 12. And 6 is 18. All right, and we have a 2 minus charge. Okay, so let's make an octet around this one. Take 2 of these. That makes a double bond here. Notice that in the valence bond theory, we have to use resonance for this one because we could have done it here, we could have done it there. Right? But does that matter? It doesn't matter. 1, 2, 3. sp2 hybridization. Okay, so A is true. The ion is expected to be diamagnetic. Diamagnetic. You know, this is not a good question either because that's a polyatomic. I wonder if there's a way to. How many electrons do we have? 4 plus 18, 22, 24. Three times 6 is 18. 4 and 18, 22, 24. Okay. Carbon and oxygen. Let's assume there's mixing and combine those two into a series of. Let's see what happens. I'm curious myself to see if what we know so far will help us with this particular problem. This says that B is true, expected to be over from oxygen. So let's write it that way. And we may not have enough orbitals, but let's see. 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16. No, that's not the right way to do it. Sorry. Let's move on. (42). How many electrons are involved in pi bonding in benzene? Okay, we can do this one. How many electrons? Total number of electrons in pi bonding for benzene. Remember, when we write it this way, we've got a pi and a pi and a pi. Right? That's 2 electrons each for each of these pi bonds. So that's 6 electrons in the pi system. All right. let's see, yeah, we can get 45 and 47. Which of the following has the highest bond dissociation energy? For this one, it's a simple matter of determining what's the bond order. The bond order will tell you how strong the bond is, and the highest bond dissociation energy is the one with the strongest bond. So the question is, of these, and they're all dinitrogens, but they happen to be one neutral and then ions for the rest. Okay, so we can use the same molecular orbital order. Sigma 2s, sigma star 2s. I 2p. It's sigma 2p. And pi star 2p. That's probably all we're going to need. 1, 2, 3, 4, 5, 6, 7. Okay, for the first one, we've got all the way up to this one. They're all paired. And the bond order is 3. We've calculated that one before. So what's this one going to do? One added electron. You add an electron here, and let me do it this way. You add an electron there, it's in an anti-bonding, it weakens the bond. It makes it 2.5. If we add another one, right, it weakens it even further by another half. This one, if we take away an electron, we're taking away an electron from a bonding orbital, which weakens it by a half. And if we take away another one, that means this one's empty now. 2 electrons from a bonding orbital weakens it further by a half. So the strongest one is this one. M2 has the highest bond dissociation energy. All right, 47. Which of the following molecules or ions does not contain a central atom with D2sp3 hybridization? D2sp3 hybridization. All righty. So the first one, xenon pentafluoride ion. All right, so we have 8 here. We have 5 times 7 is 35 minus 1. So that's 43, 42 total. Right. Xenon 1, 2, 3, 4, 5. 2, 4, 6, 8, 10. 32. We do 6 more around each one. 6 times 5 is 30. Minus 30. So we have 2 electrons that have to go here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This one is D2sp3. About B. IF4 minus. Right? These are both halogens, so it's 5 times 7 is 35 plus 1 is 36. So we have I, we have fluorine, 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 2, 4, 6, 8. It's 28. So 6 times 4 is 24. That's 4, there, there, there. 1, 2, 3, 4, 5, 6. That one is also D2sp3. 6 groups. The next one, SF6. SF6, we did that one before. That one is D2SP3. We did that one earlier. Well, actually, we did selenium hexafluoride, and they're the same thing. They have the same number of valence electrons, so they're going to come out to a hexagonal structure, D2SP3. How about D? Do we need to do this one? SEF5 minus. Okay, so we got 6, 35 plus 1 is 42. Excuse me, only 5. 2, 4, 6, 8, 10. 32. So 6 times 1, 2, 3, 4, 5. 6 times 30. Got 2. Right there. 1, 2, 3, 4, 5, 6. This one is also D2SP3. All of these contain a central atom of D2SP3 hybridization. They have 6 groups around the central atom. Some bonding, some non-bonding. All right. We're getting close. All right, we didn't do that. Okay, how about this one? What we've got here is 3 different molecules, A, B, and C. Electronic geometry, hybridization, bond angles, and examples. Okay. And we're given, this one is sp3 hybridization. And then the rest of them are different, or based upon the information that's given. Molecule A has hybridization of sp3. We're given that. So if it has sp3, it's electronic geometry. It has to be tetrahedral, 0.5, nominal. Right? There are extenuating circumstances sometimes, but that's what it should be. An example, that's not right. That's not an example molecule right there. An example of an sp3 hybridized is methane or carbon tetrachloride, right? Those are good examples. How about B? B has 2 more effective pairs. If you have 2 more pairs, where are you going to put them? You have to induce d orbitals, sp3. 2 more effective pairs, because these are all used up. You need those 2. D2sp3. Oh, I see what's happened. Those things got shuffled out of order, right? So this key is wrong. Use what we put up here instead of that. In fact, I better make myself a note. 60. Here we go. All right, so what's the electronic geometry here? If you have 6 pairs, it's octahedral. Right? And what are the bond angles? Well, sometimes I have to draw the bonds, the thing out like this. Right, with something in the middle, the central atom in the middle. So you can have 90 degrees here, you can have 90 degrees here, right? Or you can have 180 degrees. So those are the only two you can have, 90 degrees and 180 degrees maximum. And in order to do that, you have to have atoms occupying these sides. Otherwise, the rest of them are 90 degrees. So if that's the case, then you have to have something like SF6 in order to give you 6 atoms occupying all positions. That gives you 90-degree bond angles and 180-degree bond angle. And C, what's the last one? Consists of a sigma bond and 2 pi bonds. And 2 pi bonds. All right, how can we get a sigma and 2 pi's? Well, let's see. If you're going to have 1 sigma, you can only have a diatomic molecule. That's the only way to get a single sigma, right? If you have another one over here, you got to have another sigma, right? So it has to be diatomic. Now, since you only have 1 sigma, how are you going to get 2 pi bonds? It has to be a triple bond, like that. That's the only way to get 1 sigma and 2 pi's. Okay, so the hybridization has to be SP because it's a linear. It's only that's the only possibility. It has to be SP. And carbon monoxide is a good example of that. So the bond angle has to be 180 degrees and it's linear. Okay. So some of those answers are right, some of them are not right. That needs to be fixed. Okay, that's 60. I got 1 hanger on. Okay, we're almost done. All right, that was 60. Let's see. I think I got maybe 1 more. Yeah, 1 more. Okay, let's scroll down to get the question. 61. Draw a molecular orbital diagram for O2 and N2. And explain why the removal of 1 electron in O2 strengthens the bond while the removal of 1 electron in N2 weakens the bond. All right, we had an example before of N2 where we removed an electron. So once you draw the orbital diagram, and that's not shorthand, this is the full thing, energy diagram. And it's not that difficult because it's right there in useful information. You just have to duplicate it right here. So let's scroll up and get those. There we go. So that's the way your energy diagram would look if you take your and you say, okay, N2's on the left. So you draw that one. O2's on the right. Remove an electron. And down below it is the explanation. Right. So the bond order for N2 is 3. If you remove an electron, it'll make the bond order, that's incomplete. Something wrong there. If you remove an electron from N2, you're removing an electron from, let me be sure that's right. Is that what he wanted us to do? Yes, removing one electron. If you remove one electron from nitrogen, you're removing an electron from a bonding orbital, which weakens it. If you remove an electron from O2, you're removing an electron from an anti-bonding orbital, which strengthens it. So O2 plus has a stronger bond or higher bond order than O2 neutral. So you just put that in your own words. And make reference to the bond order. What does this removal of an electron do to the bond order? Because the electron's being removed from bonding orbital for one, anti-bonding orbital for the other. That explains. Okay, I think that's the last one. Let me see. Yep, that's it. Save changes, yes. All right. So everybody's gone, so this will be for the benefit of those who are watching the recording. You can either come to class on Thursday, or I'll have the exam in Brightspace. So you can take the exam in Brightspace. And it should take me no more than 24 hours to get them all graded and get your averages put into Brightspace so you can see whether you're where you made the A. If you got an A, you don't have to take the final. But if you're still a B or below, then you have to take the final. And that will also be available online. And like I said at the beginning, if your final grade reduces your average, course average, then I'll throw it out. If it improves your course average, then I'll include it. And remember, the final counts for 2 chapter exams. It has that weight. Okay, that's it.